Okay, continuing where we left off from part one. Let's see where we were. Yes, okay. So we were talking about the integrated rate law, and we just kind of finished going over the order of reactions and how to find them based on different graphs. So let's talk about half-life next. So half-life comes up just a little bit. It's not a pretty major topic, but it's important to think about. So the half-life is the time for the concentration of reactants to be cut in half. So if we take a look at this is a different graph of this is the exact same graph here, just with a different kind of diagram. So if you can figure out the half-life with a graph pretty easily, like in this situation. So if our starting concentration is 0.1 molar, we want to figure out where is that reduced by half, so down to 0.05 molar, which is right here. And the time in order for that to happen is the half-life. So in this particular situation, our half-life, circle the 0.1 and the 0.5, we go across to this point and we get 100 seconds. So that is the half-life. And that kind of keeps going. So to reduce by a further half, to go from 0.05 to 0.025 is going to be right here. And that is going to be at 200 seconds. So every 100 seconds, the concentration is going to decrease by half. This is pretty consistent with this particular example because this is a first order reactant. If it weren't a first order reactant, that would not be the case and it would be a bit more complicated. What you all have to know about half-life is that even if you don't have this graph, if you have some other information, you can figure it out. There's an equation on your sheet, this one right here, this T1/2, that means half-life. And if this is a first order reactant, then you can use this equation. So going back up here to the first order, it's right here, and you can use the K from the equation. So going back to our example here where we solved for this equation, our K was 0.0059. So if we were to use the half-life equation, we could use 0.0059. Actually, let's just run through and test that real quick. Maybe it's right. Let's find out. So according to this equation, the half-life is going to be 0.693. Oops, my calculator does not do 6 as well. Divided by 0.0059. Okay. It puts it at 117 seconds, but you know, that's vaguely in the right vicinity. It's not exact. But it's close enough that I think that we kind of are generally on the right track. But anyway, so that equation is there. So if you are trying to find the K, you could potentially even use that. Just trying to look. 0.1. Yeah. But the data would kind of give you that information. So half-lives are really useful for that. I do want to add something. Radioactive decay. Radioactive decay is a first order. I was going to say reaction, but it's really more of a process. So when we're talking about half-life is usually mostly used for radioactive substances, as radioactive substances decay over time. It's really important that they have that linear relationship because that's how we use radioactivity as like a clock, a cosmic or clock. So like carbon-14 dating is all based off of the fact that carbon-14 decays at a kind of consistent linear rate. So there we go. All right, moving on. I think this covers pretty much everything for the integrated rate laws, which again, you got to kind of do graphs and you end up with these weird equations. It's good to know that they exist, but we're not really going to use this too much. being able to look at 3 graphs and determine the order is important. So moving on, differential rate law. So this one expresses rates as a function of just grabbing a pen here real quick, a different color, of a function of reactant concentrations. So this time, instead of comparing reactant concentration and time, we're comparing the rate and reaction concentration. So a little bit different. In this particular case, the rate law is always going to take the form of this kind of equation. So it's not like a y equals mx plus b kind of situation. Instead, it is the rate, the constant, which we're going to derive experimentally, of course, and then the concentration of the reactants and raised to their order. So m or n in this case represent an order. If there's one reactant, we just have one of these. If there's 2 reactants or 3 reactants, we just keep adding more as we need them. So in order to figure out the differential rate law, and generally speaking in chemistry, when we ask for rate laws, I want this one. So this is very important, this general kind of format. This is not on your yellow sheet, so it's just kind of a thing you have to know, but you'll get used to it. Okay, so determining the order of reactants is based on again, how changing the reactants affects the rate. And there's a couple of different methods for solving this. There's the method of instantaneous rate, which we can totally use. I'll show you how to do that. It's not something we're going to do very often, but it's just kind of nice to know. And then the much more common method, which is the method of initial rate. So let's look at some data. Hey, it's the same reaction we've been covering this whole time, the decomposition of dinitrogen pentoxide. So we have our data here. This is a little, let's see, is it the same kind of data? This data is a little bit different than the previous one because instead of starting off with 0.4 molar or 0.1 molar, we're starting off with 1 molar and time continues. I'm just checking something. I'm interested for the purposes of the half-life. This time looks like it's 1,000 seconds for this particular experiment. So that's kind of interesting. This experiment is probably done at a different temperature. So one thing I will mention is that your K changes based on temperature. The other parts of the rate law actually will stay the same, but the K, if you change temperature, you're gonna have to recalculate for the constant, which would change the half-life. So there you go. Okay, so in this particular situation, oh man, that is kind of hard to read, but we'll go ahead and try to figure it out here. So we have, once again, there's a graph here that takes this data and turns it into a graph. And then this is just another graph that just shows the calculations of instantaneous rate. So we talked about at the very, very beginning of this, over an hour ago. Oh my gosh, this is taking so long. That instantaneous rate is the slope of a tangent of a curve. So if you want to know the rate at any given moment, you can do that. So what we've done here is found the rate at 2 different points. And what's usually a really good idea is to pick the rates. I'm just trying to make sure I got this. That like the rate where pick 2 points so that when you divide the concentration, you're going to get a whole number. So what I mean by that is like if we're starting at a rate of 1 concentration, pick the next concentration that's like 1/2 of that. Because that way it's like you're doubling or halving. It's the easiest way to do kind of this sort of math kind of thing. So what they've done here is they figured out the rate at this particular spot here. And they figured out the rate at this particular spot here. And this is essentially just the kind of slope of the line. And let's see, it looks like that is at, just trying to figure out the concentration here. I believe that they're going for, it looks like maybe They're not doing like 1 and 0.5, but it is something kind of like that. Sorry, just trying to figure this out here. One moment. Just taking a second to just check this. Didn't want you to have to watch me think. Okay, so I think that this is going for, it's somewhere between 8.8 and 1. So I think that this is supposed to be like at 0.9 molar. And this one looks like it's just the kind of the point that they're trying to get the tangent for is a little bit above the 0.4. So it's probably going for like 0.45. 0.45 molar. Okay, so in this particular case, the concentration at that exact moment, that instant, is 0.9 and 0.445. And the rates are also, actually, I'm going to use the other method for this because it kind of works. Well, I'll talk you through both. There's a mathematical way of like doing a calculation and setting this up that works just fine. I can kind of tend to just do this stuff in my head. So what we end up here is we have this data that at when the concentration is 0.9, the rate is 5.4 times 10 to the negative, oh goodness, is that 1? 4. So the rate, that's 5.4 times 10 to the negative 4. Now, rate is in a weird measurement. It's in mole liters per second. Moles divided by liters per second. Yeah, okay. So it's really molarity per second, which kind of makes sense. But it can also be written as mole liters per second. That's one way of writing it. Or you could do it as mole liter seconds. Those are all the same unit. Units are funky. We're going to get into that for sure. Units for constants are even crazier. Okay, so there we go. There's the rate. And then over here, it's 2.7 times 10 to the negative 4th molarity seconds. Molarities per second. So it looks like the rate has, when the concentration has cut in half, so has the rate. So therefore, we would know that this particular reactant is first order. There's another way of doing that, and it's going to be kind of similar to the method of initial rates in just a second here. What we are allowed to do is we can write out the equations, our rate laws, and we can divide them by each other. So basically, we've got our rates and our concentration. So going back to this equation, we've got rates times K, concentration raised to the M. So in these particular situations, we're trying to solve for K and for M or N or any of those other order variables that we need to. So if we can cancel out everything else or put in numbers, we can do that. So if we've got two equations, so the first one is going to be, I like to pick, we're going to be dividing the two equations. So I picked the larger of the two just to make life easier. So the rate in this particular case is 5.4 times 10 to the negative 4th. We'll put units in just because we have to. And that's going to be equal to K times the concentration, which in this case is 0.9 molar, and it's raised to the M. Okay, so again, that's based off of this formula that we're always going to use. Okay, so that's the first one, and then we're going to divide it by the second one. So that's going to be 2.7 times 10 to the negative 4th mole seconds equals K times, in this case, it's 0.45 molarity to the M. For this particular problem, what we're actually trying to do is solve for M. That's the variable that we're trying to solve for. Right now, we can, because the K is going to be the same for the reaction, because they're both happening, it's all happening at the same temperature, we can actually just cancel out the Ks. So now all we're really solving for is for M. So let's just do some quick math. 5.4 times 10 to the negative 4th divided by 2.7 times 10 to the negative 4th is in fact 2. So 2 is equal to, and the units will cancel out as well, is equal to 9. Now, here we have some interesting math. We have two different numbers that are both raised to the same power. If that is the case, you are actually allowed to divide those two numbers. So 0.9 divided by 0.45 is also 2 raised to the m. So the question now is, what number must we raise 2 to equal 2? Well, the answer is clearly 1. So if we raise 2 to the 1, it's 2. If we raise 2 to the 2, it's not 2, it's 4. If we raise 2 to the 0, it's 1, so that won't work. So what we've just done there is we figured out either through a more mathematical method, a problem solving method, or just through basic like understandings of what order is, that n is a first order reactant. So we can now write the rate law. The rate law is going to be rate is equal to K and the concentration of N2O5 raised to the 1. Because it's raised to the 1, we just don't write anything. And that's the rate law. Bam, that's it. Super, super chill, right? Okay, last step for this one is we actually can solve for the K. You don't always necessarily need to, but it's probably not a bad idea to do so. So let's do that for the next one because I'm actually running out of room here. But let's try one more of these. And then we're pretty much done. Oh no, we have to go back. Okay, perfect. So the method of initial rate, we can, it's actually this same basic procedure. In this case, instead of using a graph to get those rates, this is where you are basically doing an experiment and then you measure the rate at the start of the experiment or the concentration just at the very, very beginning of the experiment and the initial rate. So you basically do the same experiment over and over again, but you only care about the beginning first few seconds of the reaction. And what you do is you alter the initial concentrations to get numbers you need. So, you know, actually, because I just showed you this, I think we can do this example, and then there's another example. We'll do those in class. And we can also go back and, now let's solve for K. Okay, changing my mind, going back to this one. It's really this exact same method, so I think you'll figure it out. Okay, to solve for K, we just need to pick any data point we want and just plug it in. So I'm just gonna pick like this first data point. So our rate was 5.4 times 10 to the negative fourth. And I am gonna include the units, and that's molarity per second. And that's gonna be equal to K. And the concentration at that point was 0.9 molarity. So to solve for K, all I have to do is just isolate it as a variable. So it's just division. So 5.4 times 10 to the negative fourth divided by 0.9. Now, another thing you're going to notice when we do this is that the units will cancel out. So it's really important because K actually has units. Sometimes K's don't, but in this particular case, it does. Wait till more units come. You're never, these K constants never go away. If we divide both sides by 0.9 molarity, the molarities are going to cancel. So we're left with 1 over S. So let's go 5.4, I gotta turn my calculator on, times 10 to the negative fourth divided by 0.9 is going to be a pretty small number. Okay, 6 times 10 to the negative fourth. So K is equal to 6 times 10 to the negative fourth. And that would be, it's either 1 over S or S to the negative 1. And that's the units. So if we wanted to, then the rate, in that case, the new rate law, we could write we could add in the units. So those are the same thing. We tend not to, but it is nice to be able to do so and know how. So there's that. Okay. So hopefully with all of that, you can see that rate laws, again, are a mathematical expression that show the connection between the rate and the concentration of reactants, or time and the concentration of reactions, which are really all related, are similar and related to each other. So, sorry, there's like a tiny cockroach on top of my document camera. It's really gross. Anyway, it happens all the time. Okay, so let's go back to Let's go back to mechanisms. So mechanisms, we talked about how we needed to be able to find the rate law related to mechanisms. And now that we know what a rate law is, we actually can do that. So determining the rate law from the mechanism, we use the molecularity of reactants in the slow step to determine the order of reactants. So what this is telling us is in this situation, whatever the slow step is, we actually are allowed to use the molar ratios. So what this is telling us is that nitrogen monoxide and O3 are both first order reactants. And if they're both first order reactants, we don't even have to do any of that math stuff. The big idea here with reaction rates is figuring out the order of the reactants. If an order is 0, it will not show up in the rate law. Crazy. I'll find an example of that at some point. So in this particular case, the rate is going to be equal to K concentration of NO and concentration of O3. And that's the rate law. Woo. Okay. Let's talk about steady state approximations, and then we'll just do a quick, we'll just tidy this all up, and I think we're good to go. All right, so let's take a look at this example. Let's go back to our favorite dinitrogen pentoxide. That's what we've been looking at this whole time. So we now know that, let me see, just checking this real quick. Yeah, okay. At this point, we've already established that in this particular case, this is a first order reactant. But you might not kind of know that if we hadn't gone through all that work. So let's take a look here. So if we look at this particular problem, we need to figure out the rate law based on the slow step. So whatever the rate determining step is the slowest. So in this particular case, this is a weird one. It has fast equilibrium. So equilibrium is a type of, we talked about this I think a little bit, reactions that go backwards and forwards. So in this particular case, dinitrogen pentoxide turns into nitrogen trioxide and nitrogen dioxide, it goes rapidly back and forth. So they're kind of almost equal to each other. You can treat it kind of like an equal sign. Anyway, our slowest step is when dinitrogen pentoxide breaks apart, those two products react to form some other stuff, and that's the slow step. So according to this, our rate law would be equal to, these are both first order because they only show up once. It's not like N2 NO2 or NO2 plus NO2, just once. So that's NO2 and NO3. This is a problem though, because these are intermediaries, right? So if we look back at the reaction, they're not in the final, like they're not part of the final answer. NO2 and NO3, and let's see, those are intermediaries because they cancel out there. NO3, NO3. Boop, 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 boop. Just looking here. Is there an extra NO3 lying around? So this is a weird mechanism. I'm just checking. I feel like there's an extra NO3 that didn't get canceled out. Oh, there needed to be a two there probably. Okay, I may have to go back and just double check that. But yeah, okay, anyway, they're intermediaries. NO is also an intermediary. NO2, yeah, we actually need a 2 in front of this one. Anyway, all right, I'll think about that one. Yeah, nitrogen monoxide for sure is an intermediary. Yeah, we need to add this up. Yeah, if we put a 2, if we multiply that top one by 2, it'll work. It's a whole mathematical thing. Anyway, sorry, got distracted. They're intermediaries. So they are not part of the original, these two chemical species aren't even in the original equation. We can't have a rate law with chemical species that aren't actually part of the equation or aren't actually reactants in the first place. That doesn't make any sense. But what we are allowed to do is to take, using this fast equilibrium equation, we can kind of treat it like an equal sign, and we can do like algebraic substitution. So what we need to do is replace these two with a chemical species that actually does appear. And in that case, it's the It's right here. These two together are equal to N2O5. So what we're allowed to do is instead write like that. We're allowed to just replace it. And once again, in this fast equilibrium, that is a first order. So that would mean that this is also a first order. Okay. That is pretty much it. So taking a look at this, the big lessons are that no matter what we do, no matter if we are talking about like collisions and exothermic or endothermic, whether we're talking about reaction mechanisms, which is what we're just kind of looking at there, or rate laws, integrated rate laws, or differential rate laws. As soon as, if you are studying a particular reaction, as soon as you know the order of the reactants, you can figure out the rate. And it's all across the board. No matter what we did, N2O5 is first order in this particular reaction. Doesn't matter how we looked at it. So one of the next things we'll do is the back page of the notes is a review. It's another example, a different reaction, and we can go through, we'll probably do this in class or I'll make a separate video at some point that goes through everything we've learned, and you can all see that it's really just one big problem that's all connected. Other key facts to remember are that the experimental data is the most important thing. Once you get the experimental data, that is the truth of the reaction. N2O5 is a first order reactant because we know this because of experimental data. And just by going through, and studying that reaction, we can then try to figure out what's going on and come up with some sort of idea, some sort of mechanism that supports that data. Hopefully you found that useful. Hopefully it gave you some sort of perspective. I know it took a really long time, but we're just going to kind of go over this a couple more times and spend time going through each of these different parts. But I think having the whole picture all at once is really helpful, just so you can kind of see the forest and then we can look at all the trees. All right, well, good luck, y'all. And we'll talk about thermodynamics next, I think.